Okay, so let's introduce the framework for choice under risk. Which is the big topic today. So we're still going to work with a set of outcomes. As we did for riskless choice. So we'll work with a finite set x1 to xk for some finite number k. And the objects of choice in this case will be different. So we're going to look at something called lotteries or probability distributions. So a simple lottery, and you'll see why we call it simple in a moment. There's another type of lottery called a compound lottery. So a simple lottery, which will denote P, okay, looks like this. So one way of writing it would be that there's some number P x1 assigned to outcome x1. The same for outcome x2 and outcome x3 and so on, all the way through up to outcome xk. Okay, so in this lottery, you can see that attached to each outcome x1, x2, x3, and so on is a number which is the probability of receiving that outcome. So essentially, when you choose this lottery, you're only going to get one outcome, and these numbers p x1 up to p of xk describe the probability that you actually get that outcome. Okay, of course, since these are probability numbers, we need some basic housekeeping. So where let's say pxi is non-negative for all I. And what else? If I add them all up, so if I add up from I equals 1 up to k, these probability numbers add up to 1. Okay? So this is a simple lottery. So for example, let's think of a let's say a coin toss, which I could write something like this. So with probability 0.5, you receive the outcome £20. And with probability 0.5, you receive the outcome £5. Okay, so there's an example of a simple lottery. I toss a coin and there is equal probabilities assigned to the two outcomes, either £20 or £5 in this case. Okay, so that's what we mean by a simple lottery. Now the next type of lottery is called a compound lottery. Okay, and essentially a compound lottery is a lottery where the prizes are lotteries. Okay, so let's write a compound lottery. Let's use P again. Okay, so P is equal to, well, with some probability, let's say Q1, you get Q1, where Q1 is a lottery as well. Okay, where Q1 is a simple lottery, for example, up to, now there need not be K of these, there could be however many you like, so let's write QJ. So if I obtain this lottery, this compound lottery P, there is some probability P of Q1 that I get lottery Q1, okay? And then that lottery has certain probabilities of getting different prizes, okay? And then I have a different probability of obtaining QJ, in which case I get the lottery QJ, okay? You could actually think with a compound lottery, just use probability calculus to say, well, what's the probability of a particular outcome, say X1? Okay, so what's the probability of X1 under this compound lottery? Well, with some probability PQ1, I get the lottery Q1, and so I multiply with some probability Q1, I get prize X1. So that's one way I could get prize X1. First, I get lottery Q1, and then with some probability, I get prize X1. Or I could, with some probability, I get lottery Q2. And if I get Q2, this has probability Q2 of X1 of getting prize X1, and so on, all the way up to the probability of QJ. Then I get lottery QJ, which has some probability of receiving outcome X1. Okay, so this is how, taking a compound lottery, you can still calculate the probabilities of the outcomes, but they're often expressed in this way, lotteries of lotteries being compound lotteries. Okay, so let's talk a bit more about choice under risk, and why we are going to use the expected utility model. So first of all, let's denote the set of lotteries. Lotteries both simple and compound. Let's use a curly L to denote that. Okay, so we have this set. These are the objects of choice, and then we're going to assume that the decision maker has preferences, which we'll use our preference notation, over this set L. Okay, so we have preferences over lotteries, and it's natural, therefore, to extend our basic rationality requirements that the preferences are complete and transitive. So our decision maker is able to compare any two lotteries, always expressing a preference, strict preference or indifference, and those preferences are transitive. Okay, so they can put lotteries in order. Okay, now if we did this, then you could show that you would need one more assumption, a continuity assumption. The set of lotteries is now actually an infinite set, because when I assign probability numbers, I'm taking them from the interval 0, 1, which has uncountably infinitely many elements in it. So this is a much larger set now. It's a very large set compared to the finite set of outcomes. But if I added one more assumption called continuity, which we'll discuss later, I could define an ordinal utility function, a representation to say, well, if this decision maker prefers lottery P over lottery Q, this is true if and only if the utility that I assign to that lottery is greater than or equal to the utility I assign to the lottery Q. Okay, so that would be one way of modeling choice over lotteries. Now, we're going to do this, but we're going to actually restrict this utility function quite a lot more. Okay, this utility function is very general at the moment. Okay, it rules out intransitive preferences, but there are other things. Once we're talking about choice under risk, there are things that really we would like to rule out that are not yet ruled out. Okay, so let me give you one example. So let's suppose that we have a decision maker who strictly prefers the lottery P over the lottery Q, okay, and they strictly prefer the lottery P over the lottery R, and they think the lottery P is strictly worse than, so I've just reversed the preference sign here, they think it's strictly worse than a compound lottery, where with probability 0.5 I get the lottery Q, and with probability 0.5 I get the lottery R. Okay? In some sense, it seems like this decision maker just enjoys the extra stage of uncertainty here. Okay, so what's wrong with this? Well, let's think about this compound lottery here. One way of thinking it might occur is through a coin toss. So if I do a diagram like this, I'll draw a circle to denote a chance node, and then two branches coming off it, and say, well, if the coin is heads, then I get lottery Q, and if the coin is tails, then I get lottery R. Okay, that's another way of writing this compound lottery. And we're saying that this compound lottery is strictly preferred to P. Okay, now notice I haven't broken the rules of completeness or transitivity here. This compound lottery, we've only got one comparison, P versus this compound lottery. We've got a comparison of P and Q and P and R. So we can't apply transitivity here. It's not going to tell us anything. But we want to argue there's something wrong with this. So what's wrong with it? Well, suppose I start with lottery P, okay? And then I see something I strictly prefer. So maybe I give a few pounds so that I can enjoy this compound lottery instead, okay? Then, after the first stage of uncertainty is resolved, I either end up with the lottery Q or I end up with the lottery R. Now, in both cases, I end up with something where I wish I had P instead. Okay, that happens in every case in this example. So if it's heads and I end up with Q, I would rather have P, so maybe I would give some more money to have the lottery P back again. Or I end up with R, in which case I want to give some money to end up with P again. So I started with P, I gave away some money to have this compound lottery. Once it was the first stage was resolved, I ended up with either Q or R, and then in both situations I wanted to give some money to get P back again. So I'm guaranteed in this case to just keep giving money away. Okay, so this really, we want to rule this out. This is widely known as something called a Dutch book. Okay, so a book being a sequence of gambles. The sequence of gambles is constructed in a way that the victim, in this case, the person with not perfectly rational risk preferences, is guaranteed to lose. Okay, now the term Dutch here, I don't think it's because this type of bookmaking practice, I don't think it has a history of occurring in the Netherlands. I think it's because in the English language there are many examples of the term Dutch just being used to refer to something negative. It goes back to the 1600s when England and the Netherlands both had very large naval fleets and were constantly at war with each other. So it was kind of a propaganda term, I think. There's other examples. So, for example, a Dutch uncle is someone, so uncles are normally friendly people, but a Dutch uncle is somebody who gives you very frank and stern advice and isn't particularly nice to you. It's kind of very harsh with you. I believe Dutch widow is used as a slang term for prostitute. And in cinematography, even modern examples, it still persists. So Dutch angle, if you ever watch a horror film, you'll see when the moment that the heroine realizes that the killer is in the house, all of a sudden the angle of the camera gets skewed as if something is wrong with the world. And that's called a Dutch angle. Okay, so there's many, many examples. So that's why it's called a Dutch book. It's more of a slang term than anything that ever actually happened. Nevertheless, this is a pattern of preferences that is compatible with a complete and transitive preference over lotteries, but we think we should rule this out. Okay, so hopefully we agree. We're going to want to rule something like this out, which means we're going to have more axioms. And if we add more axioms, we're not just having a general utility function, we're going to work with something more specific. So we'll see that next. Now we're ready to introduce the expected utility model. The key idea of the expected utility model is that rather than just taking a utility for lotteries, as we suggested before, there is a function called the von Neumann-Morgenstern utility, which is a utility function for outcomes. Okay, so risk-free outcomes. This utility function is then used to take an expectation of the utility value for a lottery. So when I look at a lottery P, I know that I might get outcome x1 all the way up to xk. Each outcome occurs with a certain probability, px1, px2, and so on, up to pxk. When I consider evaluating this lottery, I look at the outcomes I can get and transform them using the von Neumann-Morgenstern utility function into a utility value for that outcome. I then take the expected utility of the lottery using this function, where I weight each of the utility terms by the relevant probabilities. We can use expected utility to evaluate compound lotteries as well. This is done in a very simple way. I simply look at each of the final lotteries of that compound lottery. So in this case, the compound lottery is equal to P. So if I take the expected utility of the simple lottery Q1, of the simple lottery Q2, all the way up to Qj, then I've evaluated j different expected utilities of these simple lotteries, and then I take expected utility as the expected utility of the compound lottery P. To give a simple example of how expected utility works, consider a lottery P, which is a coin toss, a 50-50 chance of £20 or £10. So probability 0.5 is assigned to the outcome £20 and probability 0.5 is assigned to the outcome £10. In this case, to take the expected utility of this lottery P using a von Neumann-Morgenstern utility function U, we would take the utility of £20 using little function U, little u. We would take the utility of £10 using this little u function, and then the expected utility would be 0.5 times the utility of £20 plus 0.5 times the utility of £10. As a simple exercise and to practice using expected utility theory, please try the following to prove that if preferences are represented by expected utility, so preferences for lotteries are represented by an expected utility where we're taking the we're using a von Neumann-Morgenstern utility for the outcomes and then taking its expectation to evaluate lotteries. Prove that if preferences represented by such a functional form are not vulnerable to Dutch books. That is, show that if the lottery P is strictly preferred to Q and P is strictly preferred to R, then it is impossible for the compound lottery 50-50 chance of Q or R to be preferred to P. P must be preferred to that compound lottery as long as preferences are represented by expected utility. Please discuss the solutions to this on the course Piazza Forum. Now let's have a look at the idea of capturing different risk attitudes in the expected utility framework. Okay, so we're going to focus on something called risk aversion in this case. So we're going to work with lotteries. Let's assume that the outcomes are monetary. Okay, so we're talking about lotteries where you can win different amounts of money. Okay, so for example, something like a lottery where with probability 0.5, you receive the outcome £20, and with probability 0.5, you receive the monetary outcome £10. Okay? So this would be a lottery with monetary outcomes. Now, because we have monetary outcomes, I could take the expected value of this lottery. Okay, so by expected value, I'm just going to say, use the normal formula for taking an expectation. I'll denote it E of P. So it would be 0.5 multiplied by 20 plus 0.5 multiplied by 10. So halfway between 10 and 20 would be £15. Okay, so this lottery has expected value of £15. Okay, now suppose that our decision maker expresses the following. Suppose that I gave them a choice and said you can either have £15 for certain, okay, so £15 with certainty, or you can have the lottery P. Okay, so you can have the lottery, let's just write this, 0.5 chance of £20. You might win more than £15, or you might win less than £15, £10, but you expect £15. Okay, now suppose our decision maker prefers £15 over this lottery. Okay, so why would they do that? They have the same expected value. Okay, so a firm, for example, or an investor should see these basically as the same. But individuals tend to express this preference, and it's because this has some risk and this doesn't, basically. That's the idea. So this £15 is for certain. This you expect, on average, £15. You might get more, you might get less. Okay, so we call this risk aversion. Okay, sometimes it's called weak risk aversion. Okay, so this is an example of what we call risk aversion. So in general, we could define the expected value of a lottery P to be a number when we have monetary outcomes. So it would be I equals 1 to K, the probability of XI multiplied by XI. So that would just be a number, an amount of money. And then risk aversion would be the condition EP, the expected value of the lottery received with certainty is preferred to the lottery itself. Okay, so that's what we mean when we say risk aversion. So what does it mean for the expected utility model? Well, if I substitute the expected utility model here, I get that the utility of 15 is greater than or equal to, greater than for strict risk aversion, equal to, we would call that risk neutrality, equal to 0.5 times the utility of 20 plus 0.5 the utility of 10. Okay, so what this inequality expresses mathematically is that the utility is a concave function. Okay, so remember a concave function would be the condition, the utility of alpha x plus 1 minus alpha y in general would be greater than alpha u of x plus 1 minus alpha u of y. Okay, so that's a definition for all x and y and alpha in 0, 1. This would be the definition of a concave function. You might also know concave functions as functions with negative second derivatives. If we have a concave function, then this inequality is true. And so the concavity, the shape of the von Neumann-Morgenstern utility function is telling us about this person's risk attitudes. In the case of a concave von Neumann-Morgenstern utility, it's saying the decision maker is risk averse. So let's sum up our analysis of risk attitudes. A decision maker is said to be risk averse if for any lottery P with monetary outcomes, we have that the expected value of that lottery received with certainty, so a certain amount of money with the same expected value as the lottery, that is always preferred to receiving the risky lottery itself. Under expected utility, this is characterized by the condition that the von Neumann-Morgenstern utility function, the little u, is a concave function. So the shape of this utility function has meaning in terms of the behavior of the decision maker. Whilst concave utility, von Neumann-Morgenstern utility is equivalent to risk aversion, there are other risk attitudes, risk-seeking behavior, which would be characterized by a convex von Neumann-Morgenstern utility function, and risk-neutral being the condition where a decision maker is indifferent between a expected value of a lottery received with certainty or taking the risky lottery itself. If the decision maker is indifferent between those two for all lotteries, then the von Neumann-Morgenstern utility function would be a affine function or a linear function, which is, of course, both weakly concave and weakly convex. So now let's discuss the uniqueness properties of von Neumann-Morgenstern utility functions and expected utility functions for lotteries. Okay, so the first thing to note is that this is an ordinal theory. So, for example, suppose we have expected utility. So P is preferred to Q, the lottery P is preferred to Q, if and only if the expected utility using von Neumann-Morgenstern function U of P is greater than or equal to the expected utility of Q. Okay? So that's what expected utility maximization or an expected utility representation means. Okay? Well, now let's suppose I take a strictly increasing function f. Okay? So if f is strictly increasing, clearly I could just take f of this and f of that, and the inequality still holds. Okay? So I could transform this. This is kind of the overall expected utility evaluation. I could, of course, replace it with any increasing transformation, and the order, the preference that's being represented is still exactly the same, as long as f is strictly increasing. Okay? So really, this is an ordinal theory. But there's a lot of confusion about the next thing that I'll say. But so this is the this overall evaluation, EU, is ordinal. But what about the von Neumann-Morgenstern function? Okay. Well, first of all, consider the following von Neumann-Morgenstern utility function. So I'm drawing a little u now. So the utility of the outcome x, let's say it's equal to the positive square root of x. Okay. Now, this is a strictly concave function. Okay. And what does that mean? So it's strictly concave. So it means that the decision maker is risk averse. Okay. Now, if I just take an increasing transformation of this, okay, so if, for instance, if I take f of z equals z to the power 4, for example, okay, then I would get f of u of x is equal to x squared, which is a convex function, okay, which would suggest risk-seeking. So just by transforming the von Neumann-Morgenstern utility function, it seems I started by talking about the preferences of a risk-averse decision maker, and now it's suggesting, so if I let v of x, a different utility, be this von Neumann-Morgenstern utility function, when used to calculate expected utilities, gives a risk-seeking attitude. This is not the same decision maker, okay? So I can't do this. I'm not allowed to just change the von Neumann-Morgenstern utility function and replace it with any increasing transformation, okay? Can I change it at all? Well, yes, you can, but there's only very specific ways in which you can do this, okay? So let's just write an example. So let's suppose that the utility of x is equal to, let's say, P, the utility of Z, plus 1 minus P, the utility of Y, something like that. So we've just got an equation. So if I just multiply everything by, let's take some number A as positive, okay? Now this equation is equivalent to saying A of Ux is equal to P times A of U of Z plus 1 minus P A U of Y, okay? This is equivalent because I can just cancel out these A's, which are strictly positive, okay? I could also take any B, a real number B, whether it's positive or negative, and I would get, let's say, A times U of X plus B is equal to P A times U of Z plus B plus 1 minus P A times U of Y plus B. And hopefully you can see here that on this side I've got B multiplied by itself once, and here I've got B multiplied by P and B multiplied by 1 minus P, so I've got B once on this side as well. So I could cancel out those B's and I could cancel out those A's, and this equation is equivalent to this equation. So if I just called this V of X, okay, then I've found a different V of Z, sorry. I found a different von Neumann-Morgenstern utility function that does the job. This is called a positive affine transformation. Okay, so affine is what mathematicians, we often say linear in economics, but affine because there's I can multiply it by a constant and also add any number you like. So positive affine transformations clearly work. That's okay. What can be shown, and we won't prove this, but it can be shown, is that positive affine transformations of the von Neumann-Morgenstern utility function are the only transformations that are allowed. Okay, so let's express this more formally next. Let's sum up our discussion of the uniqueness properties of expected utility with the following proposition. We won't prove this, but we've suggested one direction of the proof already. This is the following. If we have two utility functions for lotteries, capital U and capital V, so these are utility functions for lotteries, and if it turns out that capital U is an expected utility function using little u, the von Neumann-Morgenstern utility, and also if capital V is an expected utility form and it's using a von Neumann-Morgenstern utility function V, then these two lotteries are ordinally equivalent. They order lotteries in the same way. They represent the same preferences if and only if the von Neumann-Morgenstern utilities little u and little v are cardinally equivalent. That is, V is a positive affine transformation of U. V is equal to A times U plus B, where A is strictly positive and B is any number. There are many misconceptions about the nature of the cardinal utility used in expected utility theory. Ultimately, expected utility is an ordinal theory, but when we are using the von Neumann-Morgenstern utility function and taking its expected value to calculate the utility of a lottery, then it's the von Neumann-Morgenstern utility functions, the little u's, that are cardinal, that are unique only up to affine transformations. In 1958, William Baumol described the expected utility theory as the cardinal utility which is ordinal. This was a provocative title, and it came about because there were so many misunderstandings, and there continued to be misunderstandings about the uniqueness properties of expected utility theory. Remember, expected utility is an ordinal theory. All it's trying to do is describe how a decision maker ranks different lotteries. That is purely about the order of preferences. It is the mathematical device, the von Neumann-Morgenstern utility function, if we're going to use it in the way prescribed by the expected utility model, then we can't select that function as freely as an ordinal function. We can only choose it up to a positive affine transformation. So one quick way of remembering this, the capital U, the big U that we've used, is ordinal. The little u that we wrote is cardinal. What does this mean as we interpret the expected utility model? Well, if, for example, the von Neumann-Morgenstern utility of an outcome x was equal to 2, and the von Neumann-Morgenstern utility of an outcome y was equal to 1, of course we can say the decision maker prefers x to y. Normally, with the ordinal utility, we wouldn't say that the decision maker likes x twice as much as y. In this case, however, we might say the decision maker likes x twice as much as y, as long as we qualify this with in the sense that the decision maker would be happy to halve his chance of winning if the price changed from y to x. So it's a qualified way of describing this comparison.